Alrighty, good morning everybody. Welcome back to Real Analysis. Plan for today is to continue our discussion of cardinality, focusing first on proving the real numbers are not a countable set, and then later on we'll show that, talk about some more general properties of cardinalities between infinite sets. So I've got my usual office hours today from 11 to noon and 1 to 2, and tomorrow from 1 to 2. I posted a new homework yesterday, homework 3, which will be due in Wednesday a week from now. Don't forget, you have homework 2 due today. So make sure that I have that in my possession by the end of today. Either turn it in now in class, or you can always get it to me in office hours, or just put it in my mailbox outside my office door. Speaking of homework, homework 1. So I finished grading homework 1 finally yesterday. Pass that back. One note I make on homework 1, question 1, when I ask you how does the proof of square root of 16 irrational go wrong for 16 instead of square root of 2? Part of why it took me so long to grade this homework is I didn't know how to grade that question, I'll be honest. Because everybody had very different answers and very different reasons, some slightly better than others, of why that proof goes wrong for square root of 16. So what I eventually did in the end is I just decided to grade that one for completion. There's lots of different ways you could say that the proof breaks down for square root of 16, and I feel like trying to sift through and decide which ones I like more than others. So that one was just graded for completion, so I think everybody just got a score of 1 out of 1 on that first problem. The rest of it, though, I did grade for accuracy. I encourage you to check out your homework, see what comments I left, and I'd be happy to meet with you outside of class to talk about that more. And yeah, do that. I also have my homework 1 solutions, again, posted on Canvas, so you're certainly welcome to check those out and compare what you did with what I did as well. And I'll also do the same for every homework going forward, post my solutions usually a couple days after the due date for the assignment. Any questions or comments before we get started for today? So, given the choice between a ham sandwich and eternal bliss, what would a mathematician choose? Lou?
The ham sandwich.
Why the ham sandwich?
Because nothing is better than eternal bliss, and a ham sandwich is better than nothing.
So logically speaking, if a ham sandwich is better than nothing, and nothing's better than eternal bliss, logically speaking, that would mean a ham sandwich would have to be better than eternal bliss. All right, so let's pick things up where we left off last time then. So last time, we kind of used our definition of cardinality to say two sets have the same size or the same cardinality if we can find a one-to-one correspondence between them, meaning a function from A to B that is both one-to-one and onto. And we also were able to come up with a bunch of different ones last class. Like, for instance, we showed that the natural numbers and the same cardinality as the integers. Technically, we did that 2 classes ago. We also showed, though, that the natural numbers had the same cardinality as the rational numbers. Because with the whole spiral argument we did on the board, we were able to show that you can find a function from n to q that is both one-to-one and onto. And towards the end of class, we were doing some shady shenanigans involving sequences of 1s and 0s, which you all got. Oh, by the way, I forgot to tell you. So I played the same 0 and 1 sequence game with the next class, and since they had a lot more students, since they had like 16 students in the class, they also lost. No bonus points. Dr. Gerstel wins this time.
Have you done that game before?
Yep.
Have other classes like
Real Analysis a year ago, I did the game and they won. They know how to read me better than you all do, I guess. Also, they have an unfair advantage because they were like, I had a class in there with like 25 students, so they are much more likely to win.
In other words, if our classes hadn't been able to work together, and they knew what numbers we'd already guessed, and you didn't change the number.
Yeah, you all would have had much more likely. I actually did change the number from one class to the next. They didn't guess my original or my new number though, so it wouldn't have mattered either way. Anyways, the whole idea behind that sequence of zeros and ones is we were trying to show that if I was cheating, even in a game where I had infinitely many people trying to guess my number, as long as I could make an infinite sequence of zeros and ones, I could always produce a new number that no one in that list had originally guessed. As long as I was able to cheat. And so what I want to do today, to start things off, is to kind of go back over that argument a little bit more formally this time, and show how, and talk about how does that prove that the natural numbers and the real numbers do not have the same cardinality. So, in other words, we're going to prove natural numbers and the real numbers don't have the same cardinality. Or in other words, we're going to prove that the set R is uncountable. So, what did we mean yesterday or on Monday when we said that a set like the natural numbers, the rationals, is a countable set? Anybody remember? Matthew?
Same cardinality as the natural numbers?
Yeah, either same cardinality as the natural numbers or a finite set. A set where you could literally just point out and count out the elements of that set, even if it's an infinite set. It's an infinite set of the sort that you could just like find a way to list out all the numbers. What we're going to be doing now is we're going to prove that the real numbers are an uncountable set, meaning there's no way to, quote, write a list, unquote, of all of the real numbers. So here's how we're going to do it. And this is going to have a special name. It's going to be called Cantor's diagonalization argument. Here's what we're going to do. We're going to suppose that the set of all decimals consisting only of, in the interval from 0 to 1, consisting only of zeros and ones is a countable set. And we'll give this set name S. So what does that mean? Well, first of all, Faith. If I were to list out all the decimals between 0 and 1, like infinite decimal expansions, are there going to be a finite number of those or an infinite number of those? There's going to be infinitely many. So if this was a countable set, we would be able to come up with a one-to-one onto function from the set S to the natural numbers. So let's try and write out what that would look like. So here we're going to put elements of S. Here we're going to put natural numbers. And we're going to try and find a function from n to S that's one-to-one and onto. So, same game as we did yesterday. Matthew, give me a few zeros and ones to start.
1, 1, 1, 1, 1, 1.
All right, all ones. I'm going to make a slight tweak to what we did yesterday. I'm going to put a decimal point out in front of the sequence you just gave. So, what we're going to assume is that we have a function f that maps the natural number 1 to the infinite sequence, or to the decimal 0.11111 going on forever. Which, by the way, is going to be 1/9. Matthew actually gave you something rational. Emily, how about another one?
0.110110.
0.110, 110, etc., repeating. That's also rational. Emily Rose, how about another one?
0.11101111, 0, and then 5 ones.
That's an irrational one, but it checks out. Truman?
0.0110001.
Etc., etc. And Lydia? I need one more.
10100.
Okay. On those last two, I don't have enough information to know if those are rational or irrational. If they have a repeating pattern, then it's rational. If they don't, then it's going to be irrational. Okay, so we're going to suppose we have a function from n to s that is 1 to 1 and on to. And our function, we're going to assume, is going to map 1 to this first decimal, 2 to the second decimal, 3 to the third, 4 to the fourth, 5 to the fifth. So we're going to let f from the natural numbers to s then be a 1-to-1 correspondence given by the previous table. Find by this. And yes, I'm going to assume that we have an infinite table here and we can see the infinite decimals. We as finite lifespan human beings can't actually do these things, but we're going to suppose theoretically that this table does tell us a way to map every natural number to some element in the set S. I claim this function f cannot possibly be onto. Meaning, I claim I can find some element in S in our codomain that doesn't get mapped to by our function f, no matter how we defined it. Here's how. Point 0, 0, 0, 1, 1, etc., going on forever is not going to get mapped to by any natural number. Matthew, how did I produce this number?
You just take the inverse of every single one of the numbers in the diagonal, which means that like, if you go to that one place and every single one of those numbers that you have, then like, you know it's not going to check out for at least that one number.
Yeah, exactly. We know 1 doesn't map to this number because the first decimal of this one is different from the first decimal in f of 1. So this 0 is not equal to first decimal in f of 1. This 0, not equal to, is not equal to the second decimal in f of 2. This third 0 is not equal to the third decimal in f of 3, and so on. And what that tells us, since we have infinitely many decimal points, is that no natural number can map to, let's give this a name, we'll call this alpha. No natural number can map to alpha because you give me a natural number n, f of n is going to differ from this number in the nth place after the decimal. We can then define new alpha, an element of S, satisfying the nth place after the decimal. I'm just gonna call it the nth decimal for short, but I mean the nth place after the decimal of alpha is the opposite of the nth decimal of whatever f of n is equal to. So first place after the decimal of alpha, the opposite of first place after the decimal in f of 1. Second place after the decimal in alpha is the opposite of whatever the second place after the decimal is in f of 2, and so on. Then, what does that tell us? Well, that's going to tell us, and we know no natural number n will satisfy f of n is equal to alpha. By the way we've constructed alpha, we've shown that no natural number can map to it under this mapping. So, well, if alpha doesn't get mapped to, but alpha is an element in S, what does that tell us about our function f, Dave?
Then it tells us the function's not onto.
Yeah, because we took some element in S, alpha, in the codomain that's not in the range. So we can say, since alpha is in the codomain of f, which is S, but alpha is not in the range of f, f cannot possibly be onto, which is a contradiction. So what does that contradict? What did we show can't possibly happen, Emily Rose?
It can't possibly be onto, or
Yeah, f can't possibly be onto. In other words, what does that tell us about this statement?
it can't possibly be countable.
Yeah, the set S can't possibly be countable. Thus, the set S can't be countable, because we assumed it was and arrived at a contradiction that way. So what that tells us is while the natural numbers have the same size as the set of all integers, and even the same size as the set of all rational numbers, it's still going to be strictly smaller than this set S, only consisting of decimals between numbers between 0 and 1, and out of the numbers between 0 and 1, only consisting of numbers whose decimal expansion only has zeros and ones in it. So the set S is going to be much, much bigger than the set of the natural numbers. And then we can say since S is a subset of R, this is also going to tell us that the cardinality of the set of all real numbers must also be greater than the set of all natural numbers. Because the set of all real numbers is clearly going to have to be at least as big as the set of all real numbers between 0 and 1 whose decimal expansion only has zeros and ones in it. Well, if your set S is bigger if that set S is bigger than natural numbers, then an even bigger set, the real numbers, is also going to have to be bigger than the set of all natural numbers. And that completes our proof. That shows that the real numbers are uncountable. We finally found an infinite set whose cardinality is strictly bigger than the natural numbers.
How do we know that R is, S is a subset of R, but like N is a subset of the integers and they were the same size? So how do we know R is actually bigger than S and not just the same size? Not that it matters all that much, but do we know that?
We don't know that. In fact, R and S actually do have the same size. But that's not important. We know that, here, let's maybe say this, that the size of the set of all real numbers is going to be greater than or equal to the size of the set S, which is strictly greater than the size of the set of all natural numbers, and thus the size of R is going to be bigger than the size of N.
Okay.
That's a good question. Thank you. Slightly sorry you asked this now. That means I don't get to lay a trap later on in the class. What questions do you all have about this? Matthew?
What is like R called? Because it's like,
A set of all real numbers. Sorry, go on.
Wait, like, you know, like N's like countable, is it like just considered uncountable then?
Mm-hmm.
Okay.
It's yeah. So uncountable is going to mean an infinite set whose cardinality is not equal to the cardinality of the natural numbers.
Okay.
A set that it's not finite and it's not same cardinality as N. And no, do we have a specific name for the set of all for sets with the same size as the set of all real numbers? Sort of. Stay tuned for the next packet for more information on that. But for now, we're just going to lump it into the category of uncountable sets. Effie?
So a follow-up question, when you put, so, the, not absolute value of X.
Yeah, sorry, I kind of introduced some new notation on you mid-problem. When we talk about, like, when we have a set S and we put these vertical bars around it, we're just talking about the cardinality of that set. So this is going to be the size of the set S. So when we say, for instance, S with bars around it greater than N with bars around it, we mean that the cardinality, the size of the set S is strictly greater than the size of the set in the natural numbers.
Okay, and we know that cardinality of S is gonna be greater than the cardinality of natural numbers because there's one more value, alpha, that's not, that makes it bigger than the natural numbers.
Well, we have to be a little bit careful because technically I haven't defined what does it mean for a function to be, for one set to be strictly greater than another set. We're about to introduce that later in this class. But the idea is there's no onto function from N to S, and that's going to make S strictly bigger than N. Because if S was smaller than N or the same size as N, we would be able to find an onto function from N to S, is essentially. And you don't have to necessarily write that down. We're going to write that down more formally very soon. I have a question. Why do you think this is called the diagonalization argument? Why is the word diagonal specifically being used here, do you think?
I mean, you're moving down the rows and columns. Like you have the first integer in the first row, and you have the second integer in the same column, and it's forming a diagonal line.
Yeah, we're essentially, if we were to kind of draw a table that kind of tells us how our function f behaves, we're essentially drawing a diagonal line down through the rows and columns of this table and saying, hey, we can find a new number that we know is never going to be in this table, no matter how far down it extends, by taking a new number that's different from every decimal place in this kind of diagonal oval that we've drawn out, so to speak. So that's why it's called the diagonalization. So, why Cantor? All right, math history lesson time. So it's going to be, Cantor, George Cantor, was a mathematician in the 1800s. George Cantor. And no, I didn't misspell George. His name is spelled George without an E at the end. In the late 1800s, proved that that this argument, and basically George Cantor is known as the father of set theory. Because he's the one who basically came along and said, hey, we need a way to talk about whether two infinite sets are the same size or different sizes. Here's how we're going to define that. We're going to define two sets, infinite sets have the same size in terms of one-to-one correspondences. And he was the one who kind of proved this to show, give an example of a set R whose cardinality is strictly bigger than the natural numbers. So here's a question. Can we find a set S where the cardinality of S is going to be strictly smaller than the cardinality of the set of all real numbers, but S's cardinality is also going to be bigger than the cardinality of the natural numbers? What do you all think? Can we find a set of numbers, or a set in general, doesn't even have to be a set of numbers, that's bigger than the natural numbers, but smaller than the real numbers? A midpoint, so to speak, of the two cardinalities. Lou?
The rational or the irrational numbers.
The set of all irrational numbers. Nope. Turns out set of all irrational numbers, same size as the set of all real numbers. Not easy to prove, but you can prove that. What else? Any other ideas for sets whose cardinalities are strictly between n and r? Happy, you look like you have something you want to say.
Well, I don't think it's gonna work, but if you do something like integers plus like an irrational number, but like the thing is you can just map that, right?
The integers plus and single irrational numbers, so how about that?
Yeah, I think you can still map that.
Nope, turns out that's the same size as the integers, which in turn then is the same size as the natural numbers. If you add one element to an infinite set, you're not actually going to change its cardinality. Or any finite number of elements to an infinite set for that matter. Its cardinality will always stay the same. Which, by the way, is a little bit tricky to prove, but is something we could prove if we wanted to. So, it's actually a much harder question than it might seem. Can we find a set whose cardinality is strictly in between the natural numbers and the real numbers? Cantor said no, that there is no set whose cardinality is strictly in between the natural numbers and the real numbers. But he couldn't prove it. And then mathematicians for quite a while were actually trying to answer this question of can we find a set whose cardinality is strictly in between the natural numbers and the real numbers. And for a long time, this was arguably the most famous problem in math. Open problem in math, I should say. Problem that was unresolved. So this became known as the continuum hypothesis. Where the continuum hypothesis is that Cantor is Cantor's guess of no, there is no S that satisfies that S has cardinality strictly in between the set of all real numbers and the set of all natural numbers. Have any of you ever heard of David Hilbert? Say, if you've taken non-Euclidean geometry, the name Hilbert pops up all over the place.
I've heard of Hilbert's Hotel.
Hilbert's Hotel, strongly related, in fact, to this idea of continuums.
Is that the infinite hotel problem?
Mhm.
Okay, then yes, I have heard of that.
So David Hilbert was a mathematician in late 1800s, early 1900s. Came around a little bit after Cantor, I would say, who is commonly referred to as the last mathematician who studied like everything in math, who like was contributing and making major contributions to like every area of math you could possibly think of. So you think of like names like Gauss and Euler and Euclid as sort of being the big names in math, people who contributed to all areas of math at their point in history. Hilbert's often called like the last mathematician of that caliber. Since then, math has become so specialized that you get research mathematicians that just focus in a very, very narrow areas. But no one really these days does studies like all of math anymore, so to speak.
The number of times Cauchy's name came up in complex analysis.
Cauchy would be another one of those
Oh.
big names, I would say, yes. Complex analysis, you can't throw a rock without hitting Cauchy's something or another theorem. But David Hilbert worked on this problem, and at the turn of the century, of the 20th century, in the year 1900, David Hilbert by the way, there's a picture, before I forget, there's a picture of David Hilbert on Dr. Murphy's office door, right between his office door and Dr. Gabler's office door. Any guesses as to why David Hilbert would have a poster kind of between Dr. Murphy and Dr. Gabler's offices? Why David Hilbert would have a poster between David Murphy and David Gabler's offices? That's why. Year 1900, David Hilbert came up with a list of 23 greatest unsolved problems in math. So this would be a list that includes great famous problems in math, like the Riemann hypothesis, for instance, which is probably the most famous unresolved problem in math today, was on this list. Continuum hypothesis was number one on the list. Like the problem that like David Hilbert was like wanted to know the answer to the most of, can we find a set whose cardinality is strictly between the natural numbers and the real numbers. And mathematicians for the next like 60-ish years, this was like one of the holy grails of math, trying to find a set S whose cardinality is strictly between n and r, or trying to prove that no such set existed. In other words, mathematicians were either trying to prove or disprove the continuum hypothesis. Until finally, in 1963, Paul Cohen came along and answered the question. Does there exist a set whose cardinality is strictly between the natural numbers and the real numbers? Does anybody know the answer to this? Turns out the answer is the continuum hypothesis cannot be proven, and it also cannot be disproven. At least in the Frankel-Zermelo axioms plus axiom of choice axiomatic system. So he proved that the continuum hypothesis cannot be proven or disproven using the most famous axiomatic way of developing the real numbers and the most commonly used way of developing the real numbers up to that point, using the Zermelo-Frankel axioms. Plus axiom of choice. Which is the ZFC axioms for short. Where, if you want to know more about the ZFC axioms, you should take mathematical logic, Dr. Gabler. Matthew, you took math logic, right? Did you talk about the Frankel-Zermelo axioms in there?
No.
No? Okay, well. Take math logic and then pester Dr. Gabler. Because I assure you Dr. Gabler knows these. But the whole idea is the ZFC axioms are a set of axioms that are the most commonly used, still to this day, in looking at and developing properties of the real numbers. And what Paul Cohen came along and proved in 1963 is that he proved it is impossible to prove or disprove the continuum hypothesis. Meaning, from the ZFC axioms alone, there could exist a set S that has cardinality between N and R. There could also not exist a set S whose cardinality is strictly between N and R. It's impossible to answer one way or the other. Logically impossible. Not difficult, impossible. And Paul Cohen won the Fields Medal for his discovery of this, which Fields Medal is basically like the Nobel Prize of math. So he essentially won the mathematical equivalent of a Nobel Prize for proving this. For proving this somewhat unsatisfying answer of can we find a set that does this or not. We need, our axiomatic system is insufficient for answering this question one way or another. One thing I am pretty sure Dr. Gabler would have talked about in math logic is Gödel's incompleteness theorems. This is kind of a very famous example of how that comes into play, like that the continuum hypothesis is logically independent of the ZFC axioms. ZFC axioms cannot be used to prove or disprove it. So this is kind of a fun question in math history. Try as you might, you are going to not be able to come up with an easy example of a set whose cardinality is strictly between N and R. But you also won't be able to write a proof that none can exist either. Yeah, questions or comments about the continuum hypothesis? All right. Takes us to the end of this packet, but not to the end of our discussion of cardinality. So first of all, we need to actually explain what we mean when we say, what does it mean to say that one set has cardinality strictly greater or strictly less than another set? Gosh, get a hog of packets. And it's actually not hard to define. You could say that the cardinality of one set is greater than or equal to another set, just using the notion of one-to-one functions. So it turns out we can say that, in general, the cardinality of A is less than or equal to cardinality of B if there exists a one-to-one function f from A to B. And this is as a definition. Dr. Gersel, why does in the packet it says card of A less than or equal to card of B, but on the board you wrote it with absolute value signs? First of all, those are not absolute value signs, those are cardinality signs, get it right. Second of all, the book uses card of A less than or equal to card of B. I like the vertical bars more myself. I'm going to introduce you to them in both ways, just so when you read the textbook and you see things about card of A and card of B, you know what it's talking about. But this is but it means the same thing as the size of A, size of B, cardinality of A, cardinality of B, however you want to refer to it. But basically, we're going to say that A has a size that's less than or equal to the size of B if there exists a one-to-one function f from A to B. Which, in the case of finite sets, that would make sense. If A has, say, 3 elements in it, B can't have 2 elements and produce a one-to-one function. Because 3 elements can't map to 2 elements in a one-to-one way. There's going to have to be some overlap. Pigeonhole principle. Read mathematics contesters out there. So in order for a set A and a set B to have a one-to-one map from A to B, that's not one-to-one. There has to be at least as many elements in B as there is in A. And we can use this as a definition in the infinite case of what does it mean for one set A to be smaller than or the same size as set B. So here's a question. What do you think our definition is going to be for saying cardinality of A greater than or equal to cardinality of B? On to. And you could be cheeky and say, oh, cardinality of A is greater than or equal to cardinality of B if there exists a one-to-one function from B to A. And you wouldn't be wrong in doing that. But the way we're going to choose to define it is I'm going to say the cardinality of A is greater than or equal to cardinality of B if there exists an onto function. Function f from A to B. Where the whole idea with onto functions is that if there are fewer elements in A than there are elements in B, it's going to be impossible for every element in B to get back to. Because, I mean, this element could map here, this element could map there, but there's nothing left over in A to map to the last element in B in this case. So if we have an onto function from A to B, that means there has to be at least as many elements in A as there are in B in order for every element in B to be able to get mapped to by some element in A. And that's going to give us a way to kind of compare the size of 2 infinite sets. Is if you can find a one-to-one function from one to the other, then the first set has cardinality less than or equal to the second set. If you can find an onto function from A to B, then the cardinality of A is greater than or equal to the cardinality of B. And if you can find a function that does both of those things, it's one-to-one and onto, then that means that the cardinality of A and the cardinality of B are equal using the definition that we've been working with over here. So if you combine these, you get cardinality of A has to be equal to cardinality of B. Questions or comments about these 2 definitions? Is that a question?
No.
Okay. So let's really quick go through a proof then that the cardinality of R is strictly greater than the cardinality of N using that. The phrase in terms of less than or greater than in the packet. Forget. Less than. So we have a definition for 2 sets having the same size. We have a definition for 2 sets, one set having size less than or equal to the other one. Matthew, if you had to guess, what do you think it means to say that set A as cardinality strictly smaller than cardinality of B.
Oh, I think that means that there's probably, well, I guess I wouldn't say necessarily there's a one-to-one relationship, it's just like intuitively, if the cardinality is smaller than the other, then you, oh wait, no. Then I would say that there's no function at all that maps them to each other.
No function at all from N to R. Uh-oh, that could be a problem. So any two sets you can have a function from it. So this might feel like a little bit of a cheeky response, but when we say that the cardinality of A is strictly less than the cardinality of B, what we really mean is that less than or equal to, but not equal to. Which may feel a little bit cheeky, but that is honestly what we mean when we say strictly less than. It's less, not like a less than or equal to, wholly equal to. So in other words, you can find a one-to-one function from A to B, but you can't find a one-to-one onto function from A to B. And if you have that, then we say that A has cardinality strictly smaller than cardinality of B. Feels a little bit cheeky when you define it that way, but it actually ends up working out pretty well for us. All right. Well, we can say by Cantor's diagonalization argument, I claim we know cardinality of N is not equal to the cardinality of R. So how can we show the cardinality of N has to be less than or equal to the cardinality of R? Faith, what would we have to do if we wanted to prove this is less than or equal to that?
We have to prove that it's one-to-one.
Yeah, we have to find a one-to-one function from N to R.
Not 1 to 0.1, 2 to 0.11, and 3 to 0.111.
That does work. So the simplest example,
Just map them straight to the natural numbers again.
I was going to say just define f from N to R where f of N is equal to, I don't know, N. But yes, your example, Monroe, does work. Define function f from N to R where f of N is just equal to N. Literally, it takes a natural number and maps it to itself, but within the set of all real numbers. Let's get now early. What do we know about this function? A function that goes from N to R that just maps any natural number to literally itself. What property does this function have? Is it one-to-one or is it onto? Emily?
21.
It's one-to-one, yeah. No two natural numbers can map to the same real number because literally every natural number is mapped to itself. This is very much not onto, but it is one-to-one. This f is one-to-one, so since we have a one-to-one function from N to R, we know that the cardinality of N is less than or equal to the cardinality of R. And since cardinality of N is less than or equal to cardinality of R, but they're not equal, that's going to tell us that N is strictly smaller than R. So since the cardinality of N is less than or equal to cardinality of R, but cardinality of N is not equal to cardinality of R, cardinality of N must be strictly smaller than cardinality of R. And that's our proof. Have a good day, everybody. See you all on Friday. So on Friday, we'll kick things off with a discussion of some nice properties of cardinality. Like, for instance, we'll prove something that feels intuitively obvious, but is less obvious to prove, which is if A has the same cardinality as B, then B has the same cardinality as A. Which feels super obvious, but actually takes a little bit of work to formally prove. And from there, we're going to then talk about, so we now know that N and R are two sets with infinite sets with different sizes. We're going to focus on the question of how many different sizes of infinite sets are there? Are there a finite number of infinite sizes, or are there an infinite number of infinite sizes?
I think there are an infinite number of infinite sizes.
Why do you think that?
So like the number one.
Let me throw my chalk at you. Make sure I have your homework for the end of the day, and otherwise I'll see you on Friday.
You can blame Dr. Trelaw. I did this in my high school summer trip here.
Did he? Oh. Probably in less detail than we're doing it, I'm guessing, but.
Quick question after, so do you want the copy of the homework that has a couple of pages scratched out, so you can see the work, or do you just want the level of confidence?
I'll take the one with the condensed answers.
Thank you, guys.
No problem. Press have offered multiple homework too. Ooh, need to end the video. I'm gonna erase